You're here because you want to master Introduction to Organic Chemistry with a University of Cambridge graduate. Hi, I'm Brendan, and I'm a University of Cambridge graduate who has been teaching chemistry to many students like you over the past 9 years. I'm also the founder of the Chemistry Institution, where we have helped many students improve in a short amount of time and achieve the grades of their dreams. Be sure to check out our website in the link in the description below so that you can download a free copy of the notes for yourself and use it to run through this lecture with me today. These are the last few chapters of your secondary 4, and we're going to talk about a new kind of chemistry that you've probably never heard of before, which is called organic chemistry. What is organic chemistry? Organic chemistry is the chemistry of carbon compounds, and these organic compounds contain carbon as the backbone. Typical example is your DNA, which contains the genetic makeup of your human body. These are organic compounds that also contain carbon as the main backbone. You will also encounter this term called hydrocarbons a lot, which are organic compounds that contain carbon and hydrogen only. Every compound can be represented by a formula. Typically, a molecular formula will give you the exact ratio of your atoms. For example, C4H10, which shows that there's 4 carbons and 10 hydrogens inside this compound. You can also be using an empirical formula, but this only gives you the simplest ratio of your atoms, which is C2H5. The molecular formula is C4H10. What is interesting is if you have a structural formula. This is new in organic chemistry. It tells you the exact structure of the molecule. For example, in a C4H10 molecule, a structural formula that could represent this molecular formula is as such: CH3, CH2, CH2, CH3. And this actually tells you from the formula what the bonds are inside this organic compound. If you need more information, there's also always the display formula that you might be asked to draw in the exam. The display formula will have all the bonds drawn. So in a C4H10 molecule, CH3, CH2, CH2, CH3 would be represented by this following display formula. Another typical term that you will usually see are called functional groups. Functional groups are patterns of structure that have specific chemical properties. Some examples of functional groups include your alkanes, alkenes, alkynes, arenes, alcohols, carboxylic acids, esters, and so on and so forth. Here I will underline those that will typically be covered in our secondary 4 syllabus. Take note, in the future, you will learn more about these other functional groups as well when you are studying perhaps in JC chemistry. Next up, let me introduce you to the concept of the homologous series. If we take a homologous series of alkanes, for example, we have methane all the way at the front with a molecular formula of CH4 and a following structural formula. Next, we have ethane with a formula of C2H6, and next we have a propane with a formula of C3H8. If you see, there is a pattern in this structural formula where you're always just adding a CH2 unit inside. Here in butane, if I were to draw it, I would just draw 4 carbons in a straight chain in the same homologous series, and this would be the structure. And in pentane, I'm adding just another CH2 unit in the middle. And if I were to draw all the bonds, it would be as such. And if you look at the MR, it always increases by plus 14, plus 14, because as I'm going down a homologous series, I'm actually adding a CH2 unit as well over here. Plus CH2, and you can see the pattern of a homologous series. As such as well, your boiling point is going to naturally increase down the homologous series. This is because your molecules are getting bigger and the strength of your intermolecular forces is going to increase in this simple molecular structure. Recap on chemical bonding as well. Now, based on this pattern, this would mean that a homologous series is a group of organic compounds which have the following characteristics. It can be represented by a general molecular formula. In the case of alkanes, the general molecular formula is CnH2n plus 2 for your alkanes. What's more, they also have the same functional group, also will therefore have similar chemical properties, and will show gradual change in physical properties like melting point and boiling point down the homologous series. And your successive members tend to differ by only a CH2 unit. So a sample question you can get in the exam is to explain how the above table shows the molecules are in the same homologous series. In this very case, you just have to copy these properties of the homologous series itself. The most obvious one would say that 1. Your successive members in the homologous series differ by a CH2 unit. This is my favorite reason. Another one is that they have the same functional group. And my next favorite reason is to say that they can be represented by the same general formula. In this particular case, you have to be very specific in a very specific question. When they give you a specific homologous series, you have to properly tell the specific general formula, which is why this is my third favorite reason. But for alkanes, this is CnH2n plus 2. Moving on, we're going to talk about how to name your organic compounds, or how to tell the structure of an organic compound from the name. It's vice versa. In a typical name, you have a prefix, a parent, and a suffix. Let me explain how each of these tell the structure of a compound. The prefix is the minor functional groups on the main chain, and the positions are also told by the prefix as well. The parent is where you can find the length of the main carbon chain, and the suffix is where you find the major functional group. I know it's a lot of parts, so just let me break this down for you. For example, in 2-methyl-butane, if we break it up into the prefix, the parent, the suffix, for the prefix, this is 2-methyl. So you know there is a minor functional group called a methyl group on the second carbon of the carbon chain. From the parent, you know it's but. From here, you can tell that there are 4 carbons in the main chain. And lastly, the suffix says "ane", which means the major functional group is called an alkane. Typically, I like to start with the parent first. From the parent, you will look at the stem. So meth, eth, prop, but, which is the example we went through, pent, hex, hept, oct, non, dec. You have to memorize up to 10 carbons in the main chain. From here, you can tell how many carbons are in the main chain, and this will usually form the building block of your drawing of an organic compound. Next, you want to look at the suffix next. This shows you the major functional group priority. In a case where there are multiple functional groups inside the same organic compound, you have to follow this priority list where 1 is the highest priority. And please go and memorize this. In general, you will typically find your carboxylic acid all the way at the top, and your ester next, followed by your alcohol, and then your alkene and your alkanes. This is also the same order of functional groups that you'll be learning, just in the reverse direction. And you have multipliers too that you have to know. Typically for 1, we don't need to put mono. Sometimes when you have the same functional group that is repeated, you have to put a multiplier like di, tri, or tetra. Usually we see up to tetra only in an organic compound, and so on and so forth. With all this in place, we can move on to the steps in naming your organic compound. So as I mentioned, you always want to find the longest carbon chain first that contains the functional group with the highest priority. This is your parent. We always start with the parent. Next, the parent will contain the suffix with the functional group of the highest priority. How do we tell which functional group has the highest priority? We look at the list on the left, which shows the major functional group priority. Then your suffix will be numbered with the smallest number. I repeat, it has to have the smallest number, because in a carbon chain, you can number your carbons from left to right or right to left, 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. So you have to be very clear that the suffix needs to have the lowest number possible. When you're counting carbons and the positions, you have to make sure the suffix has the lowest number possible. And then your substituents, which is your minor functional groups in the prefix, will have the lowest numbering possible too. But it does follow the number dictated by the suffix as well. And this is typically arranged in alphabetical order. Lots of moving parts. Let me give you an example. So when I look at an organic compound, I want to find the longest carbon chain first with the major functional group. I typically like to use a highlighter to highlight this line over here. This shows there are 5 carbons inside this carbon chain. So this is a pent. The major functional group here is an alkane. So this is a pentane. And that's it, because there's no other minor functional groups as well. Next example, you have a compound like this. If I want to highlight the longest carbon chain with the major functional group, this is it. So this is 6 carbons inside. This is a hex. And from my knowledge of functional groups, this has all single bonds. So this is an alkane. So this is a hexane. Remember, there's this minor functional group over here called a methyl group. So this is a methyl group, and if I were to give it the lowest numbering possible, there are 2 ways I can count. Either like this, 1, 2, 3, 4, 5, 6 for these carbons, so it will be in the 4th position, or I can count the other way, which is 1, 2, 3, 4, 5, 6. To give this the lowest numbering possible, the answer is that it is a 3. So this is actually 3-methyl hexane. So make sure there is no gap here, and there is a hyphen between your number and your letters. Now, what if I'm trying to draw an organic compound from the name? Well, you follow the same logic. Step 1, you want to look at the parent first and find out the number of carbons in the main carbon chain, and then you draw out the main carbon chain. Then, from the suffix, you will find the major functional group and note the position of the functional group. Yes, the suffix will tell you the position as well. There will usually be a number if it's important. So you number the carbons from left to right or right to left, and then you draw in the major functional group first. Next up, you want to, from the prefix, find the minor functional groups and their positions. We will draw the minor functional groups afterwards. Make sure you follow the same numbering of the carbons that you formed in step 2. Then you want to draw all the remaining hydrogens. I want to emphasize this a lot. Please make sure that every carbon has 4 bonds. I repeat, every carbon must have 4 bonds. No more, no less. In the beginning, you will find a lot of struggles with drawing organic compounds, and you will make this common mistake. But if you take these steps in mind and listen to them carefully, you will not go wrong. Let me go through some examples to show you. First, you have 2-methylbutane. So from the parent, this is but. So I'll draw 4 carbons in a chain first. Then I take note, it's an alkane. So everything will be single bonds. So I don't need to add anything else. And then you have 2-methyl. So there's a methyl in the second carbon. This is the second carbon. So there's a methyl group over here. And last step, I will fill up the remaining hydrogens. And make sure every carbon has 4 bonds. And voila, that is how you draw an organic compound. Next example, you have 4-ethyl heptane. Hept is the parent, so there's 7 carbons. It's an ane, so it's an alkane. So there's all going to be single bonds. No need to add anything. 4-ethyl. An ethyl group is a C2H5 group or a CH2CH3 group. It belongs to the AL series, the methyl-ethyl series, right? Where you can tell the number of carbons from the name as well. Methyl is 1 carbon, ethyl is 2 carbon, right? So on the 4th carbon, which is right smack in the middle, there's an ethyl group over here. And then that's it. So you fill up the rest with hydrogens. And that is how you draw this compound. Let's move on. 3,4-dimethyl heptane 1-ol. Now there's a lot of different parts here, but if you break this down, it's actually pretty simple. Heptane, hept, means that there's 7 carbons. 1-ol means it's an alcohol, So there's an alcohol group on the first carbon. Let's treat the carbon here as the first carbon. So this is actually carbon number 1. Please take note. Then 3,4-dimethyl. So there's dimethyl means there's 2 methyl groups, one on the 3rd position, one on the 4th position. Since our carbon on the right is number 1, you have to number them accordingly over here. So there are 2 methyl groups, one on the 3rd position over here, and one on the 4th position over here. And that's it. So I'll fill up the rest of the hydrogens now, making sure every carbon has 4 bonds. That's all for today's video. If you really learned something and you like this video, be sure to click on that like and that subscribe button so you don't miss out on free content like this. If you want to join my community of students at the Cambridge Institution, be sure to check out our link in the description below so that you can sign up for a free trial class today. Here you can learn the exact systems that we use at the Cambridge Institution to help our students improve in a short span of time and also achieve their grades of their dreams in the end.